Okay, cool. All right. So thanks for that introduction, Matt. Like he said, I'm Michael Robson, former PPLer, now an assistant professor at Villanova University. So I'm going to be presenting work that I did as part of my dissertation on flexible hierarchical execution of parallel task loops, and then a continuation of that work by current PPLer, Kavitha Chandrasekar. So people who give keynotes love to talk about trends in architecture, so I'm going to copy them. So this is a slide from Sanjay's presentation at Solishan 2 years ago with data compiled by a former student, Nikhil Jain, on injection bandwidth versus CPU speeds. So you can see kind of as we move forward in time, you know, things like BlueGeneL to Summit, right? We've decreased the bandwidth versus CPU speed. So basically this means while we've been increasing performance on the nodes, the actual network capacity has not kept up, right? We saw this last year. So this is a recreation of a slide from Steve Plimpton at the keynote of last workshop that basically replicates the same idea with, you know, increasing LinPack performance and an increasing number of flops that have to be covered memory movements either from local data or remote data, right? So sort of as we go forward in time, networks become more and more of a constraining factor. So general idea is we have these deeper nodes, thinner pipes. There are a lot of reasons for that. I only caught a bit of Jeff Vedder's talk this morning, but talking about heterogeneity and accelerators and GPUs, right? And so this is contributing to it, but it's not really solving a lot of these problems. So, you know, in general, the picture kind of is, you know, we find ourselves with these nodes that are connected by an internet that are getting deeper and deeper, and we need to find a solution, right? So one possible solution that we're going to examine in this work is the idea of combining OpenMP with Charm++ and the idea of spreading, right? So the idea of spreading is flops are really cheap. You know, we have these very powerful nodes. They have tons of cores. They can do complex calculations very fast, but we need to, in sort of the Charm++ vein, inject communication as early and often as possible, right? The network is going to be our most constrained resource, and we want to use it wisely. And we'd like to have sort of a steady, continuous trickle of data and packets and information onto the network flowing everywhere, as opposed to these big bursty dumps of information that then make the network the critical path, right? So what we're going to look at today is using OpenMP to speed up individual compute loops, and then combining it with the, you know, Charm approach to get better communication computation overlap. So what might this look like in graphical form? I think this is the best way to explain this concept. So here we have two axes. One is the spreading factor. So basically the number of cores that an individual task is going to run on, compute loop, an object, whatever you want to call it. And then that's on the y-axis. And then on the x-axis is the amount of over decomposition. So basically the number of objects per core, right? So, you know, our traditional approach here would be, you know, basically one giant object that runs on all the cores, right? We know this is OpenMP. This is basically, you know, shared memory parallelism. So we start out here, right? We also have the idea of MPI, which is sort of the other side of the coin, where we basically divide the data we want to compute into separate processes or separate ranks, right? Each of those are on an individual core, but they're only running one thread at a time, right? So, you know, OpenMP and MPI, and MPI plus OpenMP exist, of course, and we'll get to that in a second, but these are sort of our two major paradigms, right? Then we have kind of the Charm approach, which introduces the idea of over decomposition, right? Instead of having just a single object per core, we can now have multiple objects. Keep in mind, this is the same computational problem, but divided up with various timelines. So these maps here are supposed to represent sort of what a projections view, an idealized projections view would look like. So in this Charm case, we take our same, you know, two-dimensional stencil, for instance, or whatever your problem is, and instead of dividing it into one object per processor, we now have 2 objects per processor, right? And obviously charm is known for, big over decomposition. This axis, extends kind of off the screen here, but it demonstrates the basic idea. So what I'm focused on is kind of this area here that's left unexplored, right? So, what happens when we have not only multiple objects per core, but also we then, use those objects to run across several cores at the same time, right? So via OpenMP. So this is kind of the, MPI plus OpenMP area. And then now we're getting into over here, the, spreading charm plus plus OpenMP combination, right? And so you can see by taking this same division of labor, right, these same 8 objects, and now by running them on 2 cores at a time instead of 1 core at a time, we're injecting data, twice as often, right? So we're hopefully going to have a little bit smoother of a curve and improve our performance, right? And this now kind of allows us this new axis of optimization, right? So, as before, charm provided this idea of over decomposition, which hopefully, by now you're familiar with. But it also allows us to, dial in how much resources are assigned to a specific task, right? So, over decomposition is not a, one size fit all tuning parameter, right? So now we can also kind of say, okay, maybe my, grain size makes sense at a certain size, but I want to have it execute faster to be injected on the network more regularly. I can't make it any smaller, but I instead can spread out that work across multiple cores. As we'll see, it has a couple ancillary benefits like better cache utilization, but this is the general approach. So to test this hypothesis, we set up a basic Jacobi application in charm plus OpenMP, ran it on a couple of machines, and then examine the performance, right? So in this case, these were built with non-SMP mode. So because of the way this prototype was set up, we had to have a separate process, and then each of those processes spawned their own version of OpenMP to distribute the work. We'll actually look a little bit later in the presentation about the work Kavitha has done to extend this, where we sort of get rid of that, but that's the case for now. All the normal optimizations, and then sort of the numbers if you're interested. This is run with a grid size that's approximately 90% of the total memory of the node, depending on the actual node. And then various block sizes so that we have a large number of chars. And we average this, for 100 iterations in most cases across 4 nodes, although we do scale it up. We also use a variety of OpenMP pragmas. So we use a static schedule to examine the performance, right? This is a regular application, right? There's no big variance in load. We will talk about load balancing at the end, and it's one specific advantage that charm has, but not something we're examining here. And we also try the collapse parameter, which we saw give increased performance occasionally and various chunk sizes. So like I said, we ran this both on Bridges, which is at the Pittsburgh Supercomputer Center, right? It's a 28-core Haswell machine with each node having 128 gigabytes of memory, as well as Summit at Oak Ridge, right, which has a 44-core Power 9 chip, along with 512 gigabytes of DDR4. I mentioned this because we actually see really good performance with big objects, right? If the objects are too small, if there's not enough work to spread out, sort of this technique isn't as effective. So if you have a lot of lightweight objects, spreading isn't as helpful, but if they sort of have, a computationally intense object, then it's worth kind of spreading it out and making that trade-off with OpenMP. So on Bridges, we ran a couple experiments. So as a baseline here, we have charm plus plus. Charm in this case has a single thread, right, per core. So this is the non-OpenMP case, and that gives us a baseline to compare against. And then we have a couple of different OpenMP experiments. So the default static decomposition, which is giving each core the total number of iterations divided by the total number of cores. So a big chunk of work at a time versus one chunk at a time in the static, one version, and then we also add in the collapse parameter. And you can see we kind of get a distribution of performance here. So by increasing the number of threads we assign to the objects, going from left to right here, with 2 or 3 threads, we're seeing in most cases, worse performance than Charm++. And then we sort of hit our sweet spot around, 4 to 8 threads, right? So each object is executing when it's running using OpenMP to run that compute loop across 4 cores. So this is on, let's see, 40 or 28 core machine. There are 7 processes, and each of these 7 processes has 4 threads. And then we are, kind of set up that way. So you kind of see there's a sweet spot here, and it will change based on, application characteristics and machine characteristics. So if we move to Summit, we see similar gains of about 20 to 30% over the Charm baseline. So in this case, we run various block sizes. So here, Charm is represented by the blue bar in all of these experiments, and then the OpenMP approach is represented by the other colors. So you can see kind of independent of problem size decomposition. So this is controlling for grain size or decomposition. Here we still get mostly improved performance. Cases like 19,000, it's a little less of an improvement in the best case. Versus say, 29,000, we see some really good improvements, right? This gap here. But in general, it's a pretty effective approach. We also examined the effects of various schedules. So in addition to, a fixed single iteration per schedule or the default number, we picked, 16 and 512. And again, see a similar approach where, we have our Charm values here with the various block sizes that were the most performant, and then comparisons with all these schedules here. And again, kind of based on a matrix of these parameters, we see the best performance here with, 7 threads in this case on Summit, a bit bigger machine, a little bit more memory, and we're able to spread out a little bit more and see more performance. We've also tested to make sure the scale, so all these experiments were multi-node, but just on 4 nodes to be able to test them quickly. But it does scale, up to 256 nodes. So this top line up here is the default OpenMP, and by default, I basically mean MPI plus OpenMP style, one big OpenMP kernel running across all the threads, and then using Charm for sending messages for the data. Then we have the default Charm approach, which you can see is much better. And finally, 2 of our best performing versions of our spreading idea with either 7 or 21 threads are able to scale pretty well. In fact, better than either the 2 versions that we have above, and also still get us that better performance, jumping down from 35% to 35-second iteration times to 28 seconds. All right, so might ask yourself, okay, well, is this some rearrangement? Is it just cache benefits, right, that a single node would get? And the answer is not really. So we reran this code on Summit without any send. We stripped out basically any of the communication parts and then looked at the performance. So in this case, here we have OpenMP, which is without any of the Charm baked in, and then also blue here is Charm, and then yellow and green are our spreading approaches. And you can see we do a little bit better. We do get some performance improvements, but they're on the order of 5%. When we actually reran this using PAPI, we actually looked at performance counters and saw we were getting better cache performance. So we kind of attribute the speed up there to just better cache behavior, right? So by spreading out the work, each of these objects is now being, subgrids of it are being computed on separate cores, so we can be stored in smaller levels of cache for faster access and less cache misses, which leads to a small amount of speed up. However, it doesn't account for, the nearly 30% amount of speed up in the other experiments. So, we're pretty confident that we're having a good impact there. And in fact, to back that up, we actually looked at the communication performance using projections. So we again ran these same experiments, collected the same data with trace projections turned on, and then looked at sort of the various time profiles. In this case, all of these are for the same experiment with different spread factors, and their timelines have been normalized, right? So I'm basically showing you over roughly the same amount of time, what does the communication volume look like across our different approaches, right? So OpenMP, not so surprising. There are these huge bursts of communications, right? We finish one iteration. Everyone tries to send out and receive a bunch of bytes on the network right at the same time. And then we do another iteration. And because maybe receives happened a little off, we're now sending and receiving a little bit earlier, a little more dispersed, but still this huge spike. And then again, a third iteration here. You still see it spread out, but these peaks are really high, right? So we're kind of really doing this bursty communication that's really making our network a bottleneck and making this a really important part for the network. And then otherwise it's totally silent, right? Like we don't care about what it's doing at all, which we've learned is not great for performance. To compare that with the charm version, you can see just by doing over decomposition, we already ameliorate some of that problem. You can kind of see there are spikes as iterations come and go, but nowhere near the same highs as the previous OpenMP only approach, but it's still really bursty, right? It's like not totally perfect. We're still kind of going in patches of injection. We want to smooth that even further. So by actually sort of continuously injecting, having objects that are running as quick as they can across multiple cores, we can smooth that even more. And now you see an almost perfectly smooth timeline, right? You can't even really tell where the iterations begin and end. I mean, there are little rises and bumps, but now it's a sort of approach where the information is sort of constantly flowing over the network. It's really being used at a low level all the time, which leads to this improvement in performance, right? And we can kind of see these all stacked together. So as a reminder, this is the charm approach, right? Which is better than this OpenMP big bursts, but is not as good as the spreading approach, right? So you can see here kind of the peaks of the blue versus the peaks of the charm, and then the peaks of the OpenMP. Okay, so that was the basic prototype idea. We got pretty good feedback, saw that improved performance, and so we started moving into integrating it into the runtime. So this is work I'm now presenting by Kavitha. This is kind of where the handoff point was, and she started taking over. So one thing she started looking at was automating this configuration of teams. So teams is a concept in OpenMP that allows you to sort of have a hierarchy of parallel task pools. And so, previously when I was running these experiments, I had to run them by hand, set up the OpenMP threads and the processes and invoke them, manually and rerun them and get all the different experiments, right? But, we're Charm, we're an adaptive runtime. We want to make these decisions automated, and we want this to be easy for the user to understand, right? So now, in addition to how many OpenMP threads am I running, we need to think about how many teams, how many masters and drones should there be, right? Basically, the number of Charm schedulers versus the number of threads that kind of run underneath them. How does this play effect with cores per processor, the total number of processors and the processes in the node, et cetera, right? So there's a lot to take into account here that we don't want the user to totally be swamped with if they're just starting to use this. So what we ended up doing here with this approach is basically fire off OpenMP to create a master thread on all of the cores. So basically have OpenMP set up a master and then spawn subthreads when we needed to do the work. This is the idea here is we want to integrate this into the load balancing framework such that, as the program evolves and executes, if we have, a dynamic case and maybe you need more or less threads per object as the program executes, you could actually sort of rearrange these master threads so you could increase or decrease their counts, right? So we can use this OpenMP nested parallelism to sort of change the ratio of masters to drones and use p threads, to kind of update the affinity of those threads as the configuration gets updated at runtime. So the idea here is that the runtime will select the best configuration after testing a couple of different combinations, basically one per load balance step, and then run with that for the rest of application. And in fact, if the application was really dynamic and evolved over time, it could retest and sort of reallocate these resources to further improve performance. So an example of this using OpenMP for nested parallelism. So this is, again, just using a static configuration schedule for OpenMP. This is on the same Bridges machine, and it compares the OpenMP performance of SMP and non-SMP modes. So if you remember previously, basically this is my approach here, where each charm scheduler, right, each PE, each master thread is a separate process, and then all of the threads running underneath that master process, spreading out that OpenMP loop inside an object, are spawned, inside the process. But within node communication, across node communication is all inter-process, right? This is especially important locally. By switching to SMP mode, where instead of having a separate process for each PE, we now just have a separate scheduler. This gets improved performance, right? So you can see basically dark blue here is charm only. Basically, there are 24 charm schedulers, 24 PEs, and by increasing the number of threads assigned to each PE and decreasing the total number, we can potentially sort of shift that ratio. But since we're running only on a single core here, we don't see much of a difference, right? Which is basically what I expect. And in fact, on the high end, when we're running with just a single scheduler and 24 threads, we kind of see decreased performance, showing that over decomposition, kind of somewhere in the middle, is the best approach, right? So then taking this approach further, where we're using a single process in SMP mode, and then spreading it out using this Teams approach, we can look at its performance on Stampede. So this is now a multi-node sample. So this is on the Skylake nodes. It's a 4-node run. And now you can see where the Charm++ approach here is in dark blue is pretty good. And in fact, is better than just the OpenMP approach in dark orange, but is not as good as this light blue approach, where we kind of hit the sweet spot, right? So with right about 6 threads per PE, that the ratio of 4 master threads in this case and 6 worker threads, that gives us the best ratio of performance and is able to, again, decrease our runtime from on the order of 50 seconds per iteration to 35. So pretty big improvement there. So how do we do this? So this is some sample code Kavitha has from the OpenMP implementation we're doing in Charm right now. So basically, she modified the machine.smp file, machine-smp file, to have each thread go ahead, or sorry, to have each scheduler go ahead and spawn a parallel section, right? And so we set the number of threads based on some input number to create here, and then we get our thread number and then call the start function to actually begin execution. But now the entire program is basically nested inside a parallel section. So our workers are already created. And when we hit an OpenMP block, like this OpenMP parallel 4 inside this Jacobi example that we've been running, we can automatically farm those loop executions out to these already created threads, right? So basically we have these master threads started by the runtime at the beginning of the program. And then when they encounter these blocks, they can automatically assign the work to their sort of sub drone threads or their worker threads as needed. So this configuration has both a static and dynamic option, where the static option basically uses OpenMP style affinity to, in this case, if there are 8 cores, set affinity and then bind those processes in a spread fashion. Whereas we'll look at in a second, we can in fact instead do dynamic configuration via the pthread set affinity call. So the pthread affinity, if we look at that performance, so again, this is process-based approach. The OpenMP. So this is using the standard GOMP style affinity, and then pthread affinity gets similar performance to the process-based and OpenMP-based implementations, or OpenMP affinity implementations, barring some NUMA effects. So the reason we want to do this, though, is that with OpenMP, nested parallelism can't change the configuration dynamically. Basically, if we want to grow or shrink the number of master threads and worker threads, that's not something we can dynamically change. Instead, if we use pthread affinity, when we change the number of masters and workers, we can actually reset their affinity such that they're correct for when we grow or shrink those pools. So with charm and OpenMP, pthread affinity sort of lets us do this update over time. That's kind of our ultimate goal. Right, so here we can select the best configuration, which is this one here. So next steps and things kind of that we're working on now are basically integrating this approach into the load balancing framework so that it's fully automated. So right now we can dynamically set this configurations at runtime based on user input. And it lets us, it's better than the static configuration, which I showed earlier, because we can change this at runtime, but it's still not totally automated, right? We can't change this in the middle of the execution without intervention from the user. We also plan to look at the CK loop implementation, right? This is sort of the charm native approach to spreading out the work of loops as things execute, and see the performance differences there. So in summary, the idea of spreading, right, taking an object and spreading it out over more cores to inject more often, offers a new optimization parameter. And as we saw, kind of early prototypes showed it increased performance on the order of 20 to 30%. This spread factor now in charm is controllable at runtime. And we're ongoing efforts to basically integrate this more deeply into load balancing. So it's totally automated and just another thing that sort of charm delivers to the user without their intervention at all. All right, so I think I'm about on time here, and I will wrap up now and take questions. And so this is both mine and Kavitha's emails. In case you have a question, don't get to ask it now. Thanks for listening.
Thanks, Michael. I think we had a question by Phil, if you want to go ahead.
Hi. So first, a quick one. Which OpenMP runtime implementation is this using? The native one from like the compiler, or the one that's built into Charm++?
This is the native compiler OpenMP runtime. So this is like a orthogonal work to Jamin's OpenMP tasking charm library stuff. That's yeah, good clarification.
Yeah, and you mentioned that you can control your spread factor dynamically at runtime, but it sounds like you're tying that to load balancing activation at like a per time step kind of boundary. For more sophisticated applications like NAMD or Changa or OpenAtom that have like lots of different computations in any one time step, would it make sense to change that factor even like within a time step, depending on what kind of work is predominant?
Potentially. So if Kavitha is here, she can chime in with her thoughts as well. I mean, it's just not something we've studied about the overheads of how quickly we could, spawn new master threads and thread pools and reassign the work. But if assuming the overhead is low enough, yeah, no reason you couldn't do that. I mean, the other thing is you could, if it doesn't make sense to spread it to extra cores, say you want some to go on 4 cores and some to go on 8 cores, right? You could spawn, enough master threads so that you have 8 threads available at any time for an operation. And then, per entry method, right, you could assign it, okay, this one only needs 4 cores, but then you're losing out some of your computational units as it executes. So yeah, I mean, it's definitely an interesting idea to explore, and like a good next step of how quickly can we do this and reassign work and improve performance.
Cool, thanks.
I can add something, Michael, to that.
Yeah.
This method when you change the number of masters, you basically are performing an implicit migration of chars. Not implicit, I mean implicit for the programmer, but they are actually migrating to these master threads. And then they have a domain of drones to spread their work to. That's the way by which this current method works. What you want can be done with CK loop easily. To do with OpenMP is a bit tricky, and we haven't thought. I mean, basically, I would even and then Harshita's method of task stealing. So those are competing ideas there. And then, of course, using, you said, Jamin, I think it's Sun Myung's OpenMP LLVM implementation, kind of the same way Bolt does it, is to use user-level threads and trick LLVM into thinking of those user-level threads as p-threads, and then use our runtime to spread that work to different cores. So there's a kind of collection of methods there that we need to find the right combinations to explore.
Are there any further questions?
You had a performance data that didn't look good. I think when you had, like, if you can go back to the thing which said the dynamic, compared the dynamic set thread affinity method.
I think this one here.
Yeah, you have that red circle on that, first of all. So then the optimal is at the charm end of things. That doesn't sound good. It should be in the middle. But even otherwise, all the bars on that right set are worse than the bars on the left two sets. So there is something.
Yes, you're not wrong. I would answer your question, but this is data Kavitha gave me, so I don't totally know what's going on here. I mean, other than I think this is kind of what we had discussed privately about using p-thread affinity lets us have more flexibility at the cost of some overhead.
I think that maybe, I mean, you can say that, but I think the real answer in my mind is that we need to look at this more and to see where this overhead is coming from and fix those sources of overheads so that it can match or do better than the one on the left. And then we can claim, yes, we have flexibility and we get performance.
Yeah.
Kavitha,
my other idle speculation or wild guess here is that if we changed the block size, basically the over decomposition, like maybe the objects are too small and so the overhead is eating into our performance here. So we had less number of larger objects, we might see a different trade-off. But yeah, no, it definitely bears, this is what Kavitha gave me yesterday. So we're still, very fresh numbers that still need more examination, like you said.
Yep, that's what I wanted to bring forward. This hopefully should get better.
Any other questions?
I don't see any, so I think this concludes the session. Thank you again, Michael, for the presentation.
Thanks.